Hello friends, this is Vilas Patil here and I'm from Hybrid Automation Technology. Today we are going to learn how many components in the RS Logix 500 software and how to program the ladder logic functions. Now let's start with the hardware and softwares used for this. Hardware is MicroLogix series and software used can be RS Logix 500, RS Logix 5000. Uh, there are MicroLogix 1000, 2000, 1200 series are there. Okay, now how to create a new program in RS Logix 500. Here, clicking RS, opening RS Logix 500 software, you'll get a window like this. In this window, you have to click on a new button. When you click on new button, one result will appear. In that you have to specify a processor name and you have to select a controller model and all, and finally select the driver and click on OK button. Then you will get a result like this. This empty area, white space, is your workspace, and this uh, list indicates the controller type and input output files in different operation files. Okay, now let's see which are the components available in uh, the ladder diagram programming. First of all, this icon indicates the new rung. This tab will help you to add a new rung above or below the current rung in which you can add a normally open, normally close contacts, on, off, OSR, OSF to create a program according to your requirement. Okay, new rung. To add a new rung, you have to click on this button. Now, if you go for a dual starter programming, okay, one will be normally open and normally closed. Normally open can be set as start button and normally closed can be uh, a stop button. Parallel to the normally open contact, you have to use one normally open contact according in parallel to the start button. Okay. For that purpose, we have to take one parallel branch out there. So we can take a parallel branch by clicking on this button. Okay. First, you have to select a proper NNC contact to which you are going to take a parallel branch. Next will be a normally open contact or XI if this is normally open node. When it is closed, we have to examine whether either it is closed or not. Okay, that's why it is called as examine if closed XIC. The instruction also called examine on or normally open functions as an input or a storage bit. If the corresponding memory bit is 1 on, the instruction will allow the run continuity and output will be energized. For example, if you take one normally open contact at the left side and normally, sorry, one coil at the right side. Okay, when normally open contact is triggered or if it is set to 1 or on, it is being closed. Then the signal from left side to flow through the right side through the coil and coil will be energized. That coil is will be your output. Okay, next is your output energize OTE. Okay, this instruction sets the specified bit when run continuity is achieved. Means run goes true. Okay, just now I told you an example. At the left side we are using one normally open contact, and at the right side one OTE coil. That can be a OTE, output energized. Okay, if the input side is closed, then output will be energized. Under normal operating condition, if the set bit corresponds to an output device, the output device will be energized when the run goes through. Okay, when the input is high, output will be high. When input goes to low condition, at that time output also goes to low condition. Okay. Next warning is that never use an output address at more than one place in your logic diagram. Always be fully aware of a load represented by the output coil. Okay. You cannot specify the multiple output coils in a single program with the same address. That that is the condition note here, or it will gives an error. Definitely gives an error. Now examine if closed. If previously I have told you an example of a dual starter. One is a normally open contact and one normally closed. Normally open called as a start button and normally closed called as a stop button. Okay. For stopping or discontinuing the rung, we have to use one the normally closed contact. That can be this XIO. Examine it open. It is normally closed already. It is to be examined if it is open. Okay, this instruction also called as examine off or normally close functions as an input or a storage bit, same as a XIC. Okay, if the corresponding memory bit is a 1 on, the instruction will not allow a run continuity and output on its run will be de-energized. Reverse of that XIC. Okay. Next is your output latch condition. For a dual starter, you will be having the two inputs. One is the start button and one is stop button. When you press the start button, output will remains high even though input is low. Okay. When you press the stop button, output goes to low condition. Uh, that's all. Okay. To achieve that, you can use the output latch and output unlatch here. OTL instruction. This instruction functions much same as the OTE, output energize, with the exception that once the bit is set with an OTL, it is latched or on. Now, once a OTL bit has been set on or 1 in the memory, it will remain on even if the run condition goes to false condition. The bit must be reset with the OTU instruction. OTU instruction will be unlatch instruction. Okay, note or warning you can take. If the event of a power loss occurs, any OTL controlled output device will be energized with the return of a power if the OTL bit was set when the power was lost. Before losing power, if the OTL bit is set, okay, after returning the power also it will remains on condition only. For that purpose, you have to take a special care whether to use it or not. Okay, you can use an latching program also. So in next tutorial I will tell you about a different dual starter and star delta starter. Okay, now this is the OTU, output unlatch. Okay, to unlatch the OTL we can use this instruction or use this component. Use this output instruction to unlatch or reset a latch or set bit when which was set by a OTL instruction. The OTU address must be identical to the OTL address which is originally set by the set the bit. Okay, if you have taken a for OTL if you have taken O colon 0 by 0, then to unlatch the set bit, unlatch the bit, you have to take a OTU instruction, OTU bit, and specify the same address as for the OTL, that is O colon 0 by 0. For example, now already you have seen XIC and XIO opens. Here for sample, we can take one example that I colon 1 by 0 1. Okay, in the sample address, I indicates the input image table. Okay, 1 represents the slot 1 in terms of decimal. After the slash, the 01 indicates the bit 1. Okay, from slot 1, from input slot 1, the first input is used or address for that particular slot or bit. Okay, if we use I colon 0 by 01, the first 0 will be indicated first. If we use 0 here, 0 is reserved for the processor. If the processor having any any inputs, then we have to take it as a 0 by 01, 0 by 0, 0 by 02, 0 by 03, like this. Okay, the input address are specified to the bit level only. Now, addressing of IOs. In an output address such as O colon 0 by 0, O colon 4 by 03, O indicates the output image bit, or actually we have to take their file, but I will explain for this scene. In an output address such as O colon 4 by 03, O indicates the output image table, 4 represents the slot 4 in terms of decimal, and third indicates the from a 4 slot the third output bit it represented. Okay, and 0 is reserved for the processor, as I told for exam for input also, same as input. Okay, in the event of a power loss, any OTL controlled output device will be energized with the return of power if the OTL bit was set and power was lost. You have to take care about this. Okay, here you can see the example for dual starter. We have two inputs, normally open and normally close here. Okay, when we press this button or trigger this input, the output is high, we have to release it again. Okay, when we trigger this and see here, normally close here, the output goes to low condition, because the latch was the signal was flowing from this run, and it is disconnected by opening this normally close button. We have taken this as a stop push button, and this is a start push button. I can see here. This is a simple example for a dual starter here, and the equivalent example using a latch and unlatch bit. When this input is triggered, it remains on condition even though input is low. Okay, when we trigger this unlatch instruction, output goes to low condition. You can see here O colon 0 by 0, O colon 0 by 0. Both the address are same. But when this input is triggered, O colon 0 by 0, I colon 0 by 0, output is latched, and I colon 0 by 1 is triggered, output goes to off condition or unlatched. Here we can see some simple electrical circuits and their equivalent ladder diagrams here. We can see here one simple series switch, series lamp here. Okay, along with an DC source. When we operate that switch, the lamp will glow. Okay, lamp will glow. We have to specify the equivalent ladder diagram for this here. The equivalent ladder diagram will be like this. Here, normally open contact I have taken here, and one output coil is there. When input is triggered, output goes to high condition. When input goes to low condition, output goes to low condition. Simple as that. Simple series circuit here. Okay. Now let's study some logic gates using the LD program ladder diagram. Okay. In the list from gates, first gate will be NOT gate. When input is low, output goes to high condition. When input goes to high condition, output should be low. For this purpose, we have to first draw a simple electrical equivalent diagram here, and this is how the diagram will be. Here we have taken one normally close push button. You can say it as a stop button also, Along with that, we have taken one lamp and we have used one DC source here, 24 volt and 0 volt. Okay, now what will be the equivalent ladder diagram for this? This will be the equivalent ladder diagram. Here you can see normally close contact I have used. When I have not triggered this, when I colon 0 by 0 is not triggered, output will be in high condition. Is energized. Output is energized. When it is uh, triggered, NC is going to be open and it will be off. Output will be off. Now OR gate. OR gate itself indicates that when it has two inputs, either I0 or I1, or both inputs are high, output should be high. For this, we have to draw an electrical equivalent diagram here. Simple electrical circuit will be like this. Two parallel switches, normally open switches, are connected in parallel, and along with a lamp, in series with a lamp, and to a source. When I0 is triggered, the supply will flow from this, or circuit will be completed from this I0, and lamp will be on. If I1 is triggered, circuit will be completed to I1. When both are triggered, current will flow from both switches and lamp will glow. All four conditions are satisfied here. This will be the equivalent ladder diagram here. Two parallel normally open contacts. Here you can see, if you want to take a normally open contact parallel to this normally open contact, you can use this run branch here. Okay, previously I told you. Next gate will be NOR gate. NOR gate is, its truth table will be like this. Okay, when both the inputs are low, output should be high. Either input is high, output should low. Okay, simple electrical circuit will be like this. Two normally closed switches are connected in series with a lamp. Okay, when I0 or I1 is open, circuit is going to be open. Both switches are open. Output will remain in off condition. When both are not operated, means it remains in normally closed condition. Output goes to high condition. Okay, here you can see both the both the inputs are normally closed, means it allows the signal from left side to right side, and output going to be energized. When we trigger either input, either I0 or I1, NC is going to be open, normally closed contact going to be open, and output goes to low condition. Next gate is AND gate. AND itself indicates that both I0 and I1 should be high to make output high. And a simple electrical circuit will be like this. When both are connected in series and both switches are normally open, and simple electrical circuit will be like this. Two normally open contacts are connected in series along with the output coil. You can see the result over here. I0 is triggered, I1 is triggered, I0 is off, I1 is off. You can see the status of output here. Now next gate will be NAND gate. NAND gate is inverted output of AND gate. Where when 0 0 means both the inputs are not triggered, output should be high. But when any one of the input is triggered, any one of the input is triggered, output should be output should remain in high condition. When both inputs are triggered, output should be low. Okay, simple electrical circuit will be like this. One condition you have to check, like check like this: both are low, output should be high. But any one of the input is triggered, output should be high. Okay,
and circuit will be like this. Two normally closed switches are I have taken here, and one lamp is connected in series with this parallel combination. When I naught is triggered, now it is in 0 0 condition. 1, it is been it is satisfied. When I naught is triggered, sorry, let's take I1 is triggered, the circuit will be completed through this run. This I naught. When I naught is triggered, the signal will flow from I1. When both are triggered only, the output is going to be low condition. All the conditions are satisfied here. Now let's see the equivalent ladder diagram. Two normally closed contacts uh, and one coil I have taken here. You can see the result over here. When both the inputs are triggered or made one, then only output is going to be false condition or off condition. Now XOR gate here just you have to concentrate on these two conditions. First, second and third condition. Second and third condition here. 0 1 and 1 0. 0 1 and 1 0. 0 when input is 0, output should be high. When input is high, output should be high. Means one should be normally closed and one should be normally open. And for third condition, when input is high, means normally open, normally closed, output should be low. But we have to specify only one out. We can take only one coil of Q0, or we can take it as a O colon 0 by 0 as the output address. For that, we have to take one parallel branch. In one branch, there are I0 and I1. Two contacts are there. Okay, the circuit will be like this. Okay. When I0 is 0, I1 is 1. Means we are making this 1 means we are closing this. Okay, 0, 1, circuit is complete, output is high. Okay, 1, 0. 0 means we are not operating this I1, and I0 0 means we are, sorry, 1 means we are operating this switch, and signal will flow from this term. Okay, and output is high. Now let's see the equivalent ladder diagram for this XOR gate. This is the equivalent XOR gate ladder diagram here. Now 1 0, output is high. Now 0 1, output is high. For 0 1 and 1 0, output is high. Now condition is 1 1, output is low. 0 0, output is low. Okay. XNOR is a reverse of XOR gate. Here you have to again consider there is only one output, but on conditions are two. Only one output and on conditions are two. For that purpose, we have to take only one coil, but there will be a parallel branch of a two contacts. Here you have to select I0, I1. Both are closed and both are open. Okay, now let us consider the circuit as it is. 0 0 means we are not operating these two switches, but these are already closed, normally closed, and output is going to be energized. Okay, now when we make I0 and I1 1 1 means we are operating all the switches here. We are operating I0 means this will be closed and this will be open, and this will be closed and this will be open. Means now the circuit is completed through this run, but this will be getting open. Now let's see the equivalent ladder diagram for the XOR gate here. Here it is. Now two normally closed and two normally open are in parallel. Now let's start with the different blocks used in a ladder diagram. First, we start with the ONS. ONS is a one shot. It is like a trigger. Here you can see in the run we have used one ONS. For example, you can take a address like this P3 colon 0 by 0 0 by 1 like this. Okay, when we trigger input, it produces a pulse at the instant when input is going to be high, and the pulse duration will be in terms of microsecond, and it is high for only one scan cycle. Okay, this bit can be used if input remains true for a long time, but we require just a pulse from it. It can be used along with the address of a counter timer example. Okay, for example, if counter output bit address can be given when counter output is high, at that time its output is going to be high. Okay, like this. Now here you can see the waveform for this ONS. Input is high at this instant. You can see its output is going to be high for only for a microsecond. Now OSR is just like a ONS, but OSR takes a two address, but ONS takes only one address, and ONS only can be used in between the run, but OSR can be used at the right side of the run. It consists of a storage bit and output bit. Storage bit indicates the status of the input. If input is high, B3 colon 0 by 0 address will be high. If input is low, storage bit is also low. But we have to consider about output bit here. Okay, when input is high, same as that of the ONS one shot, it's B3 colon 0 by 0 is 0 by 1 also goes to high condition for only microsecond only. Okay, you can see here I am triggering this I colon 0 by 0, and we can see the B3 colon 0 by 0 and 0 by 1 status here. B3 colon 0 by 0 will remains on in on condition until and unless I colon 0 by 0 is high, but B3 colon 0 by 1 is high, will be high only for microsecond, and output will be energized for that instant only. Here you can see the waveform for that OSR. Now OSF, it is a reverse of that one shot falling. One shot falling in the sense when we release the input at that instant, its output bit will be high for a microsecond only. Okay, now its the input and output waveform will be like this. When we release the input at that instant, its output is going to be high. Here you can see some example here. I am triggering here I not continuously. P3 colon 0 by 0 is the storage bit. It shows the status of input. Input is high, storage bit is high. But when I release the input at that instant, B3 colon 0 by 1, which is the output bit of OSF, it is going to be high for a microsecond only. Okay. Now timer off delay. Sorry, T on. Inserted a wrong picture over here. Let's see this T on, timer on delay. Okay, here you can see timer address will be T4 colon 0, and for next timer address you can take a T4 colon 1 2 3 like this. And time based value is nothing but just speed of a time you can set here. Here I have taken time based value as a 1 here. Okay, 1 into 5 is 5, means your output time delay will be 5 seconds. If you have taken a 0.01 here, 0.01 means 0 0.01 means 1 by 100. Okay, 1 by 100 in the sense 1 by 100 into 5 is equal to 0.05. To specify a 5-second time delay, you have to specify a 500 in this preset value. Okay, and in preset value you are specifying the time delay value. Accumulator value will be display of timing. Okay, counting of a time. When the input is high, accumulator value starts counting the time. 1, 2, 3, 4, 5. When it reaches to the preset value, its output is going to be high. Here you can see the enable bit here. Enable bit is also like a storage bit here. When the input is low, enable bit is also high. When it reaches to the accumulator value, reset it starts counting, and when it reaches to the accumulator value, done bit is going to be high. And you can take the done bit address like a t4 colon 0 by dn. Okay, this will be the done bit. For time enable bit, you can take it as a en. Okay, one more special bit is there, tt bit, timer timing bit. I will explain in the next slide. Use the t on instruction to run an output of on or off after the time has been on for the preset time. This output instruction begins timing at either 1 second or a hundredth of a second intervals. When its run goes true, it waits the specified amount of time as set in a preset. Okay, keeps track of the accumulated intervals which have occurred. Okay, and sets the dn bit done bit when accumulator value equals the preset time. Okay, here you can see uh, waveform for the input and output waveform for this t on delay. Here you can see this will be the preset value. Okay, okay, this will be the preset value. This is our input value, input waveform, and this is our output waveform. Here you can see input should remains at least for a preset value or accumulator value. When it reaches to the preset value, accumulator value reaches to the preset value, output is going to be high. And further you can see when input goes to low, output also low. Okay, input goes to low, output also low. This is the done bit here. Okay, one more special bit is there, timer timing bit. Means when t on starts counting or accumulate value starts increasing 0, 1, 2, 3, 4, 5 until it reaches to the preset value, its tt bit will be high. Okay, this is a timer timing bit. This bit can be used in a traffic control lights and all. Okay, uh, okay friends, thank you for watching this video, and keep watching, and subscribe and like my videos and subscribe my channel. For motivating me, I'll keep on uploading such wonderful things on my channel. And wait for the next part in which I'm going to show you